We now start our discussion on the logic gates that we have already mentioned before, such as OR, and NOT. But in addition, we have others like NAND, NOR, XOR, and we have symbols that represent this. We normally say that the output of the gate is a logic 1 if the logic signal satisfies the logic operation described by the gate. And therefore, if we find ourselves with an AND gate A and B, if both of them are on, then we say that y is equals to 1 because the two input variables have satisfied the logic expression AND, which is described by the gate. So the symbols used in the description of these gates are as shown. The AND, OR, NAND, and NOT gates can have more than two inputs. So we see the symbols that we use to represent all the 6 gates that we have encountered. We normally represent the AND as such, the OR as such, and the NOT as such. And the other 3 are just modification of the first 3. What you observe is that you can be able to draw this one very simply as half a circle with 2 inputs. That is how we normally draw it if you are drawing it by hand. Very simply, that is an add operation. And if you are drawing an OR, we normally draw it with that 2 inputs, but again we notice that it can have more than 2 inputs. The inverter can be drawn as a triangle with a circle at the other end. That represents an inverter or a NOT gate. And finally, when we are drawing the NAND, we just draw an AND gate with an inverter symbol, or rather as a circle at preceding the output. So this is your NAND operation. How you draw the OR or the NOR operation is same way you draw an OR, a curved input with a circle preceding the output, and your 2 inputs get in there. And finally, how you draw the XOR, the 2 inputs are, or the input is preceded by another curved surface like I have drawn. Therefore, this becomes your Y. So this is your NOR operation. This is your XOR. Sometimes we write it as XOR or with a preceding XOR. So those are the symbols that we use to represent the logic gates that we are going to be using in this course. So just get used to those symbols, identify them very easily, and also observe the operation that they represent. So whenever you see an AND, you are noticing that Y is the output of A, B, and you have the dot, and this is your A and B. Always the input are on this side and the output is Y, and you can be told what does Y represent. It represents an AND operation. Now in this case, an AND operation, which is inverted AND, and NOR represents an inverted OR. So if Y was A or B, now because we have NOR, we have an inverted OR operation. And finally, XOR, we normally use the symbol Y is equals to A XOR. We use a circle with a plus inside. That represents an XOR. So that is a brief introduction to the gates, and the best we can do is to memorize them. These are symbols we are going to meet over and over again in this course. For that reason, you should get very familiar with what each of those symbols represent. So we start with the AND gate, and we see that the AND gate gives an output Y at logic 1, if and only if, that is the condition, both of them, both A and B, are at logic 1. So we say Y is equals to 1 if and only if A is equals to 1 and B is equals to 1. And we normally use a truth table to represent that kind of a relationship, in which we say what are the values of Y when we have different values of B. Such a table that represents that relationship between the output Y and the input variables A and B is referred to as a truth table. Since the logic variable A is either 0 or 1, and also the logic variable B is either 0 or 1, for a 2-input gate, there would be 4 possible input values, that is 0, 0, 0, 1, 1, 0, and 1, 1. And for such a reason, for such a case, then we would ask ourselves, what is the value of y when A is a given value and B is a given value? So we normally draw a truth table in this form. We ask ourselves, if A is 0 and B is 0, what is the value of y? We say that the condition is not satisfied, then we say that y will be 0. What about when one of them is a 1? Again, the condition of AND is not operation, because we said AND operation is satisfied when both of them are at 1. So 1, 0 also will give us a 0, but when we have both of them as 1, that is when we have the output y as being 0. So this final now shows the truth table of an AND operation, just like we have developed it. Now we look at the OR gate. The OR gate gives a logic 1 if at least one of the inputs is a logic 1. That is the condition or when the OR operation is satisfied. If you say that the NOT, first and foremost, NOT gate only has one input and the output is at logic 1 if the logic is at 0 and vice versa. So if in case you are taking our input through an inverter, which is also called a NOT gate, then if you had A is equals to 1, then the output here will be 0. And if in case it was a 0, then the output here will be a 1. That is the logic operation of NOT gate. OR gate is similar to, OR gate has two inputs, minimum A or B, and we are saying that if either of these is a 1, then the output will be a 1. If none of them is a 1, that is only when y will be a 0. The NOT gate is also referred to as an inverter, and that I have already said with symbol I and V. The NAND gate gives an output at logic 0 only when all the inputs are at logic 1. I think here we missed a 1. So we say that the NAND gate operates opposite of what AND operates. We say that our AND operates will give us a 1 when both of them are at 1. But now when we make it, when we invert our NAND, our AND become NAND, then we are saying that it will be output logic 1 when either A or B are 0. Then NAND gate gives an output at logic 0 only when all the inputs are at logic 1, which is opposite of what we have seen in AND gate. So if we just redraw our AND gate to the table here, and we say we have A, B, and Y. If this is our AND operation, then our NAND operation will be opposite of that. So this will be 0, 0, 0, 1. Our NAND operation will be 1, 1, 1, and 0. So we are simply saying that our NAND gate gives us a 0 only when all the inputs are at logic 1. That is when we get a 0 from the NAND gate output. It can be observed that the NAND gate is equivalent to the complement of the AND gate, and hence that is the name. It is called NAND or not AND. So here we have the truth table of our OR gate, like we did with the AND gate. At least one of the input is at logic 1, then our output Y will be at 1. That is when we have the last three rows. Because at least one of them is a 1, then we are getting a 1 at the output. But when both of them are at 0, then our Y output will be a 0. We look at the truth table for a NOT gate, and you can see that when we have input is 0, our Y will be a 1. When we have input is a 1, our Y will be a 0. That is what we have said. That gives us the opposite of what is at the input. So if we have 1 at the input, we get the opposite of that, which is 0. And now we have the truth table of our NAND gate, and we have already developed this one. We had first and foremost developed the one for AND, and we say this will be 0, 0, 0, 1. And therefore, because it's opposite of AND, becomes 1, 1, 1, 0. Now we look at the other remaining two gates, that is the NOR and XOR, and we say that the NOR gate has a logic 1 output only when all the inputs are at 0. Again, we are going to be comparing it with our OR. We assume we have inputs A and B, and our OR Y become coming out of OR, and Y becoming out of, or Y prime becoming out of NOR. So what we do is just say, look at all the 4 possibilities, 0, 0, 0, 1, 1, 1. So we have said that all says at least one of them is a 1. So we saw 1, 1, 1 here, and without any 1, we get a 0. So null gives us opposite of that. So this becomes 1, and all these others become 0. That is what it means, that the NOR gate has logic 1 only when all the inputs are at logic 0. Further, the gate derives its name from the equivalence of the negation of the output of OR gate. Therefore, because it's like not OR, that's why we are getting the NOR. Finally, we look at the XOR or exclusive OR. It says that it performs a modulo 2 arithmetic, and the output of the gate is a logic 1 if the inputs are of different logic levels. So what we say, and we say that this is now XOR, sometimes we indicate it as such, and we are saying that when the two are different states, when the two inputs are in different states, that is when we have 1. Otherwise, if they are the same, we get a 0. And we also have another one called XNOR, which is not very common, but we can say this is the opposite of this. It gives a 1 when both of them are the same, and 0 when they are not. So this would be our XNOR, but the one that we are looking at this case is this XNOR. It performs modulo 2 operation, and you'll find the meaning of that at a later date. So this is what we have developed. This is the truth table of NOR. It will give us a 1 when there is no 1 at when both of the inputs are at logic 0, that we have seen. It is opposite of OR. And similarly, for the XOR, we are saying we are only getting 1 when they are having opposite signs. So if one of them is 0, the other one is 1, it's exclusively 1. That's why it's called XOR. And when the other one is 1 and the other one is 0, that is when we have a 1. Quite significant.